Hi everyone, I'm Konstantinos. Welcome to another Oxford Physics event. Today, join me in welcoming Professor Mason Porter. He will be talking about opinion models and social influence on networks. This may not immediately seem connected to physics, but I think once you hear the talk, you'll realize the correspondence with it. So we're very excited about this talk. And again, thanks for joining us from LA. So Professor Mason Porter, ex-Oxford University professor, currently at UCLA. And yeah, I think you can get started, Professor.
Okay. So thank you very much for the invitation. I appreciate it. I still try to visit Oxford every summer. Obviously, last summer, this didn't work out, but hopefully, maybe even this fall, depending on how things go, or at least next summer, I will spend some time. I'm still technically a visiting professor in the Mathematical Institute, deeply embedded in the website somewhere, and I'm also still a senior research fellow in Somerville, where I was tutoring applied math. So shout out to Somerville if anybody from Somerville is here. Okay, so I'm going to talk about opinion models and social influence on networks, and as was indicated, I'm going to try to give a connection to why this actually is connected to physics. I agree the title does not make it obvious. A sort of very short answer is that some of the tools that people will use when studying it are analogous to tools from statistical physics. So you've got, instead of having a lot of particles, though, you might have a lot of interactions with, say, humans who are interacting with each other. But there are various ideas like thermodynamic limits and other things from statistical physics that will get used. And I'll try to bring those out. And people actually often publish a lot of this work, and myself included, in physics journals. Okay. Let me actually not go through it so much. We had a short course on complex social systems. So if you end up wanting to look that up, we have a bunch of lectures there and so on. The last bit was an advertisement from the short course, but that's more before. Okay, so spreading fake news on social networks. So these are fake news. This here is actually a character from my childhood, from a show. His name is Gary Gnu. They actually pronounce the G with a hard G for the name of the character. So spreading fake news on social networks. Okay, we're going to think about that a lot. All right. There are a lot of different types of models, and the models take different flavors, both mathematically and physically. And the main thing that I actually want to do with this talk, as sort of by way of introduction of people studying things along these lines, are three different types of models. And I'm going to just illustrate how they work just through specific things that my collaborators and I have done with them. So I'm not going to go into a lot of detail, but I want to give you an idea of a flavor of them. And one type is known as a threshold model, which is actually, it takes a flavor of something that's known as percolation, which is something that people both in the mathematics literature through probability and in the physics literature have studied a lot. That's probably not a buzzword that you've seen in your courses yet. That does, but it's a well-known subject within physics, and this particular type of model has that sort of flavor. There's something called a voter model. Voter models are actually not models for voters, despite the name. And you can have ones where the states, what the opinions of the people in it are coupled or interacting with the structure of how they're connected to each other. So that's one thing there. And then there's something called bounded confidence models. And the notion of bounded confidence comes from social psychology. And one difference between these sorts of models and these other two, this has discrete states, 0 and 1. This has discrete states, so say left and right or whatever. And this has continuous states. So people's opinions will be continuous between 0 and 1. And when they interact, they will compromise by a certain amount if their opinions are sufficiently close to each other. So it takes a different flavor from some of the others. Okay, so let me give an introduction. All right, so social networks, and they can be different sizes. Okay, so you could be talking about one college, which would maybe be 500 people, but you could be talking about interactions on Twitter where you're talking about, many millions of people, right? So they can take different sizes. Usually you think of each, so it's called a node or a vertex, that represents an individual. And then the edges, right? So a network consists of nodes that are connected to each other via edges. The edges are some kind of interaction. It could be offline interactions, LOL, or it could be phone calls, Facebook friendships, Twitter followerships, actual other like genuine interactions, commenting, and so on. So there's various types of interactions, and there's a notion both of a social connection, but also a notion of people communicating with each other. And these things are tightly intertwined, sometimes very hard to separate them. Different things will propagate on different types of networks as well, if you're thinking of some sort of process that's occurring on them. So today we'll talk about a certain process occurring on them. People also study network structure for its own right, for various reasons, like trying to find functional units in biology, for instance. So if you think of like information spreading, this is going to spread offline and online. But if you think of like disease spreading, this will only spread offline. And so when people talk about physical distancing, the idea is exactly to adjust the network structure to inhibit the spreading. This is exactly a network problem. And insights from, in that case, disease spreading, have in fact informed various policy. You can argue about whether they've informed them well or not. That's another story, but they've informed them. I'm going to skip the last part because I think it'll take me too long to explain. I have a booklet, which at some institutions you can download for free, but if you go to my website, you can find it anyway. As a short booklet. It is written for people who know a little bit of dynamical systems, which I don't remember the exact numbering now, but might be Math B 5.6 in the Oxford math numbering. So it's a Part B level course in the math department to get an introduction on it, and that would be already sufficient to read this book. I don't know the comparable course in physics, but this should be a book that is self-contained, maybe a little challenging, but self-contained. That would be a good way to get started. There's also a book written by a physicist, Mark Newman, on networks in general, which is written as an undergraduate book, which would also be it's a larger set of topics and a little wordier, would also be a great place for you to get started. Okay, so if I have some sort of process that occurs on a network, so I've got these individuals and they're interacting with each other in some way. So I've got a dynamical system on a network. It could be a disease model, it could be a model for information propagation, it could be a bunch of lasers and you're going to see if they synchronize, could be any number of things. And the basic question that people ask, and again, think of this physical distancing type of intuition on policy, is how does network structure affect some process that occurs in the network? And sometimes people will also ask the reverse question, because maybe if people have certain states, right? If someone tests positive for COVID, they better stay home. The network structure therefore changes, right? So the coupling can actually go in both directions. So this is meant to be a booklet on it. It's 70 pages, but it's 70 lecture note size pages. So it's pretty short. Okay, I'm not going to go through this whole slide, but there's a general point that I want to make. And the reason is that a bunch of papers tend to be implicit about this, and it's useful to be explicit. You can think about whether the states of the individuals are changing, infected, uninfected, and so on. And you can also think about whether the structure is changing. And there's a question about timescales. This is very much a physics type question, right? It's a question about timescales. What are the relative timescales at which a network structure is changing versus what are the relative timescales at which the states of the objects, of the nodes, are changing? And how you treat the system in a mathematical way depends on these relative timescales. So, for instance, if the states of the nodes are changing faster than the network structure, it may be reasonable to treat the network structure as fixed, pretend it's fixed, and only look at the states of the nodes. And then conversely, maybe the network structure is changing much faster than the states of the nodes, so maybe you want to concentrate on the change in the network structure. Okay, so those are sort of two extremes. There's other stuff in there, and this is a bit of a dense slide that you can read about, and I think it's like a 2-page chapter 6 in the previous booklet if you want to look at it in more detail. But the point is, if I say I have a network structure that does not change, and I put something on top of it that does change, I have made an implicit assumption on the timescales of the system. Okay, so today we're going to talk about spreading and opinion models, or contagion opinion. There's different names for these. They have different flavors. There are more than just these 3 types, but then again, I'm going to use this as a way to give you an introduction to the field more broadly. So a threshold model, remember this is percolation-like, and this is a type of model that has discrete states, usually 2, so uninfected and infected, or inactive and active, or spin up and spin down if you prefer. And this models what's called social reinforcement, and it does it in a minimalist way. And the basic idea is that I maybe hear rumors from different people in my friendship circle, not that anyone in my friendship circle would ever start rumors, but I hear rumors from different people in my friendship circle, and I may treat these as independent things. And so if I hear it from more than one person, it may help convince me. And that's different from disease transmission, which usually you can say, well, this goes from person 1 to person 2 because of their specific social contact, right? So you're kind of surveying your neighborhood instead of looking at a specific social contact at a time. And the rule for updating a state of a node is a simplistic way of trying to capture that. There's something called a voter model. These also have discrete valued opinions, but instead what you're doing is you're looking at a pair at one time, and if they have a different opinion, then they're known as discordant. You have some probability of, say, flipping a weighted coin for one of them to change their opinion, and you try to ask questions like, well, how long does it take to reach consensus and things of that sort. And then there are these bounded confidence models. So the term bounded confidence comes from social psychology. I'm actually just starting to co-supervise a PhD student with, so this professor is a professor of philosophy at Hamburg, but I know him from, we were both at Somerville. So we actually know each other from Oxford, and apparently bounded confidence models are also a thing in a certain part of not just social psychology, but other parts of psychology. And so there's a nice Oxford connection where you can literally co-supervise, a mathematician can co-supervise a PhD student with a psychologist, which is, quite, or the philosopher, which is quite an amazing thing, right? Like, Oxford connections really help for stuff like that. Okay, so here's an example of threshold models and Physical Review X. There's this paper by James Gleason that has some examples of other models that also satisfy some of these properties. So this slide's a little dense, but it will hopefully help convey how these models work. And so there's a particular model that's sometimes called the Watts threshold model. It was actually invented before Watts. And it works as follows. So I have a network that does not change in time, static network, and each node J has some threshold. Okay, so R indexed by J, so there's some parameter that each node has. I draw it from, say, a distribution. Maybe it's from a Gaussian distribution. That's a common choice, or I make all of them the same. And this represents a sort of stubbornness or a latency. So we're going to want to overcome this for them to go from uninfected to infected, go from state 0 to state 1. And I pick some nodes from the network, maybe uniformly at random. You can pick a seed number or you can pick a seed fraction. Those nodes start at state 1. So the rumor is starting, or the disease is starting at those nodes. And then we're going to have a rule for how nodes go from uninfected to infected. And the rule for this particular model is that I compare my fraction of infected neighbors. So K sub J is called the degree of node J. So this is the number of friends I have, or maybe the number of people I'm following on Twitter. So that I see these people in my feed, and some fraction of them are infected. And I compare that to my latency if I'm going to be updated. And if it meets or surpasses my latency, I will go from uninfected to infected. Okay, so that's how this model works. The generalizations of this model tend to, so this M over Kj is like a peer pressure, basically. So it's peer pressure versus stubbornness. And so the generalizations of this model will either, change the stubbornness and make it more complicated, or they'll change the peer pressure and make it more complicated. Those are the two things that they tend to do. And then as a technical point, you can either update synchronously or asynchronously, and maybe that's something that we can talk about later if you're interested. And in this particular model, and this is a part that's unrealistic, though you can ponder if there's any situations in which you think it might be okay. Once you go to state 1 in this model, you stay there forever, okay? That's going to be different from the other models that I'm going to show you. So one of the things that can happen is that depending on who is infected first, you may get different amounts of infection at steady state. So in this particular example, and this slide was stolen from my former postdoc, Sergey Melnik. He did his postdoc with me when I was still at Oxford. If I start with the middle node infected, and I suppose that this threshold is 0.3, so I need 30% of my neighbors to be infected for me to become infected if I'm being considered. And so if I start with only the middle node infected, eventually everybody becomes infected. So the fraction of infected states is 1. If I start from this node only infected, then 5 out of the nodes become infected. And if I start, and the reason is that if I look at this node over here, it has 5 neighbors, right? And it has a threshold of 0.3. So if this thing's infected, that's 0.2, and that's less than 0.3, and therefore this does not change. And there's no way for that to ever happen. So it's actually a fundamental roadblock if no one out here is infected, right? So different initial conditions will lead to different levels of steady state. Typically, you need to run many realizations, which means different choices of initial conditions, and you would have, well, mathematically, or in the language of statistical physics, you would have an ensemble average over those if you were going to do some theory, and then numerically you would compare that to a sample mean. As a sort of technical point, if you want to actually see how good one of those theories are, you might want the number of nodes in your network to be large. Like this is a really small network. This is smaller than what we usually consider. But you might want the number of nodes to be reasonably large so that you can actually compare that theory in a good way. The downside is if the nodes are larger, especially if you're doing many realizations, the computation time is large. So there's a bit of a tension there. Okay, so one model that we did was to generalize this by putting hipsters. This is with my, actually, Jonas Yule was a visiting master's student who visited me at Oxford, and he's now a postdoc at Cornell with Steve Strogatz. And the basic idea is that we wanted to look at a situation where, so there's some intuition where, you know, anti-establishment results seem to occur more often than one might think. And my idea with this sort of paper is that I think that intuition is not correct. And that it's possible for these sorts of results to occur more often than people think. And what we wanted to do was that we wanted to construct a simple model in which this occurs, not necessarily the main amount, but that it occurs pretty generically. So there's a large set of parameter space, right? So basically looking at phase diagrams in the language of statistical physics, bifurcation diagrams in the language of applied mathematics. And we want to say, okay, there's a large range of parameter values where the anti-establishment can win, and that it can happen generically in this model. And so, you know, we argue that people maybe should be a little less surprised than they are when this happens in real life. Okay, so the way this model works, you've got most of the nodes are conformists, and they follow exactly the same rule that I described in the last slide. But some fraction of the nodes are hipsters. So when it's their turn to update, and the rule that says, I am going to update now, the condition to actually update is the same, but what they do with the update is different. And in particular, instead of looking at their local neighborhood, they look at a bestseller list with some time delay, and they adopt whatever is in the minority in the bestseller list. Okay? All right, now this slide I won't go through completely, but again, I'm just going to give intuition. So first of all, let me just show one of these. This is tau equals 5, so the bestseller list is tau 5 units ago. This is using discrete time in this particular model. It is on a type of graph known as a 5 regular configuration model network. What that is, 5 regular means everybody has 5 friends. So we suppose, and this is not realistic, that everybody has 5 friends. And we connect those friendships uniformly at random. Okay, so the randomness comes in because of who's connected to whom. Okay, and the vertical axis is the adopted fraction at steady state. So this red one means, for instance, that over here for this parameter value, about 90% of the nodes adopted red at steady state, and about 10% of the nodes adopted blue at steady state. Okay, the horizontal axis is the fraction of hipsters, or the probability of a node being a hipster in the network. And so if I'm over here, 40% of the nodes are hipsters. If I'm over here, 20% of the nodes are hipsters. And so one of the things that actually happens with only 20% of the nodes being hipsters, we actually find that the initially minority product so A or B, the initial minority opinion actually ends up winning out, getting 70% or 75% of the final adopted fraction. So there's this large range of parameter values over here where this happens for this particular family of networks. The intuition is the following, and it won't exactly happen this way, but we get, in a sort of more stylized version. Let's suppose I have, so this is a tree where each node has 3 children. So this is known as an infinite Cayley, it's known as a Cayley tree, and I believe it's called a beta lattice in physics. But Cayley tree is, anyway, it says it's a tree. So let's suppose I have this initially infected node, and let's suppose that on this branch I have a hipster right in the first one, and then I have no hipsters later. So I have a small probability of hipsters, and it turns out the hipster shows up in this spot. So this hipster will adopt the less popular product, and everyone after him in this entire branch will also adopt the less popular product. So the idea is that if you have one of these nodes, these hipster nodes, even if there's very few of them, in a place with a roadblock, that can lead to a large number of adoptions of a less popular product, or how an initially less popular product can win. So the idea is that situations like this, though in a messier form, occur in this other type of network as well, and in some others that we study. That's kind of the intuition of why this can happen. Okay, so moving on, as I promised, I just wanted to give flavors and not to go into full details. That particular paper is like 20 some odd pages if you want to see more of what's in there. But hopefully this gives an idea of what we're thinking about. Okay, so voter model, the voter model. The is in quotes because there's actually variants that make important differences, but it's still called the voter model. If you want to look up and find out what people have done with this, I think the first reference that I would go, this is by Sid Redner, who's actually a very well-known physicist, used to be at Boston University and is now at the Santa Fe Institute. And he has a mini review of reality-inspired voter models, and this discusses different things that people have done. The main thing behind putting the in quotes is that if I choose a random node and update it by comparing it to one of its neighbors, that gives one kind of family of results for how long it takes, say, to converge to a consensus. But if I choose a random edge and then choose one of the 2 nodes at the end of it, that gives a different result, and the timescales are different with those choices. So that's not the only choice, but choosing a random node versus choosing a random edge is the main sort of difference in how you would formulate it from a technical point of view, and then you can generalize either one of those in different ways. Okay, so in a voter model, what do? You either pick a random edge or you pick a random node. If I pick a random node, I will also pick one of its neighbors at random, and I will compare those 2. And it may be that they have the same opinion, and then I do nothing, but it may be that they have a different opinion. I would call this a discordant edge if they have a different opinion. Okay, so I may be 0, they may be 1. Most studies of voter models have 2 opinions, but there are a few that have some larger number, and it's discrete states. Okay, so maybe instead of being 0 and 1, it'll be -1, 0 and 1, or something like that, right? You can have different versions of it. Okay, so I compare me to my neighbor, and if we're different, I update, something like that. Or if I pick a random edge, and it's discordant, then I'll do 50-50, and one of those 2 nodes will update. Okay, so we're going to use, and there's a particular paper that one of my recently graduated PhD students and I published last year in Physical Review-E, so same journal as before. So we use edge-based updates because we found it easier to pick a random edge. One of the reasons random edges can be useful to pick is because edges are what have the property of being concordant or discordant. And if you're measuring consensus, you want to measure, it's a very natural, a physicist would use the term order parameter, but it's a very natural thing to track the number of discordant edges, right? So you might imagine the vertical axis would be the number of discordant edges. How often do you get a 0 connected to a 1? And we used asynchronous updates, which means we're picking one of these at a time. Okay, so we did an adaptive version. So what this means in practice is that we couple it to the network structure. And we want, so if I have a discordant edge, there's two things that can happen. One is that it will turn into a concordant edge because someone will change their opinion, say from A to B. The other possibility is that, and then think of the, and maybe this happened more with US-based people, but think of the contentious arguments on Facebook, like during the 2016 and more recently 2020 election. Instead of coming to an agreement, maybe you'll just, you'll unfriend the person or something because you can't put up with this crap anymore. Not that that would ever happen. And then you rewire in one of three different ways. In our paper, you can rewire to a random node, which means you still may create a discordant edge, right? So I'm A, I may rewire to B. I can rewire only to someone else who's also A, or I can just not rewire at all and just unfriend. From a technical point of view, in terms of, so rewire to none was directly motivated by unfriending, and there are a few papers that have considered that. From a technical point of view, if you're trying to do some analytical theory, that's actually harder because there's certain, you lose a conserved quantity. Basically, this rewiring has one less conserved quantity, and so it actually in certain, it's not necessarily intuitive, but okay, not having a conserved quantity and then being harder, that should make sense, right? Because you're used to that because you're physicists. But the fact that unfriending should be harder than rewiring to a random thing, if you don't think of it that way, may be less obvious. Okay, so with some probability, we break a discordant edge and either rewire or unfriend, depending on which variant of the model we're studying. And with a complementary probability, we update the opinions in following a standard voter model. And then it happened to be the way that we did this is that we have a probability of sigma to the q of doing a rewiring and a probability of 1 minus sigma to the q of doing an update. And this q is this nonlinearity parameter. When you start finding transitions, so q ends up being our parameter that we tune. So think of it as changing the temperature or changing the pressure. Q is what's playing that role in this particular paper, and we look at whether there's a phase transition as we change this particular knob that we say we're allowed to change. So it's a more abstract knob than in a physical system, but we're thinking of it in that sort of way. Okay, so just to give a schematic of one move, just to understand what we do, and then I'll give you an example of stuff that we did in there. We have a discordant edge, which means that I have A adjacent to B, right? They disagree. And I have some probability that, so I'm going to choose who's going to adopt. So I have to choose whether A or B are going to adopt. So I flip a coin and I say, suppose A is going to be the one who's adopting. And if A is the one adopting, it will become B in one step. And then with complementary probability, it will rewire. And then there's three different rewiring strategies depending on the variant of the model we use. So maybe it rewires to this node, right? So you have steps like this, and you ask yourself towards the end, do I achieve consensus? Or does the network fragment, right? In this case, the network could actually break up into echo chambers. So here's one thing that can happen. The type of network structure we started on is known as an Erdos-Renyi random graph, which means, so capital N is the number of nodes, and we were probably considering something like 500 for most of these simulations. I'd have to look this up. And P is the homogeneous uniform probability for two nodes to be connected. So I have two people, and I flip a weighted coin, and with probability P, they're connected, and with probability 1 minus P, they're not. And I generate a bunch of graphs this way. So each one realization has a graph that was generated in this way. So this Q is the horizontal axis. So I'm thinking of this like a temperature. And as an example here, the vertical axis is the terminal density of the minority state. So I take T goes to infinity, and I ask myself, well, what fraction in the minority? And if Q is small, right? So Q is small. So I'm going to have 1 minus sigma to a small number of adopting, so sigma to a small number of rewiring, right? And then, oops. So then I'm going to get close to 0.5 in this terminal density, but then if Q is large, I end up getting a small fraction. The reason that this fraction is not 0, but it's just small, is that there are going to be some clusters of echo chambers that get disconnected that will still be in the minority state. So that's why it does not actually go to 0, but goes to a small number. And then on the right, and I realize, these are showing, it's showing dense plots which would, without the whole benefit of the paper to read it carefully, right? So the same horizontal axis. Now I'm showing here the terminal density of state A. Okay, so whether or not A is in the minority or majority, I start, and I should have said this earlier, the initial condition is that half the nodes are in state A and half are in state B in this particular plot. So there's no favoritism of one versus the other. Each blue is one run. Okay, so every blue is one simulation. And every black is a sample mean of all the blues for a given value of Q. So I think there might be 20 different, I think for each value of Q, there might be 20 different things, maybe, I don't know, I'd have to check. And the black is a sample mean. And there's a lot of scatter. But what happens in general, if Q is small, there's not a big minority, right? There's not a big minority at the end. But if Q is large, either A wins or B wins, right? And these black reflect the relative fraction for a given value of Q of how often A wins, how often B wins. And this is scattered because it just depends on the particular configuration initially. So that's what that's trying to show. If you have different network structures, you can have more complicated phase transitions. I think I'll leave that slide at that. So you can look at majority illusion and echo chambers. So let me just briefly say what that means without actually going into much detail. So the idea behind, echo chamber, I think you understand intuitively at this point. What majority illusion is, do I survey the entire network? And if I survey the entire network, I find that there are more white nodes than red nodes. Or do I survey only my neighborhood? And if I survey only my neighborhood, maybe I may find that there are more red nodes and white nodes among my friends, right? So it's looking at what your Facebook feed looks like, which is your neighborhood, versus a survey of the entire population. In social science, there's something called homophily, which is, the birds of a feather flock together, like of the same. People tend to form friendships with people who are similar to them in some way. And what this is going to imply is that a situation like a majority illusion, where most of my friends are red, even if most of the world is white, forms very naturally from essentially principles of how friendships form. So it's easy to construct a network that can do this, but the deeper fact is that you expect them to form based on natural processes. An example of this where I felt this very keenly, in the 2016 election of Clinton versus Trump, early in the day, I'm seeing all these posts on Facebook with all my friends in my Facebook network, posting with their votes for Clinton because, politically they are, very similar to me for the most part. And so I'm seeing all these posts. But then when you start measuring the entire polls, of course, it's different from what was occurring, right? So what you see in your echo chamber, in your feed, versus the entire population are often very different from each other, and it forms very naturally that way. Okay, so we see things, I'm not going to go through this slide, but this is to say we see things like this, manifestations of things like this in this model that we studied. And you'll need to look at the paper if you want to do that, because this will just take too long to explain in any reasonable way. So I will instead go to the third type of model to continue giving you a flavor on this. These are called bounded confidence models. And they have opinions now on a continuous space. So -1 to 1 is a common choice, but you can normalize and you can make the space multiple dimensions. So you can think of having a space along a libertarian authoritarian axis and also a space on a liberal conservative axis, or you can put as many dimensions as you want. You can also put a quality dimension, and I'll show you an example later. So let's pick two entities of these nodes to interact. So we pick that at random or something. And if their opinions are sufficiently close, so there's going to be some parameter that measures what it means to be sufficiently close, they will compromise by some amount. and the amount by which they compromise is some other parameter. And otherwise, their opinions don't change. And so that's this particular bullet point is what a bounded confidence mechanism is. This comes from social psychology. If you're sufficiently close, we will compromise, and otherwise we won't. And so maybe the compromise is, maybe this toy is supposed to represent actually having a discussion and hashing out the issues and so on, although we instantiate it mathematically as just a number updating. The two best known variants, one is in asynchronous time and one is in synchronous time. They date from about 20 years ago. So they're also a little bit, voter models, by the way, are half a century old. So these are a bit younger. They were initially studied, if you actually look at the papers by these authors initially, they were initially studied to look at how extremism that comes in, small amount of extremism might come into a population and kind of invade it and become a predominant opinion. That was the sort of original motivation for the model, but actually that's not usually what's been studied during the last 20 years. Usually what's been studied has been whether consensus is achieved and how long it takes to achieve it, which is maybe the easiest mathematical question to study, but not what we're seeing in society with schisms and so on. And so what I've been trying to do with these models is get more in the direction of trying to study some other facets, although it's not so easy. And then traditionally they were studied without network structure. And so another thing for people to think about is to put in different social networks within it and ask how this changes things like the convergence time to consensus, or how many groups there are as t goes to infinity or whatnot. Okay, so we have a paper. This comes from, actually, this originally was an Oxford paper. That this was the 4th year project of mathematics student Flora Mung a few years ago, and then she went to MIT for grad school. Robert Van Gorder was a departmental lecturer, I forgot the terminology, within the Mathematical Institute, so he was also there. But yeah, so this comes from an Oxford undergraduate project, this particular paper, and it was a sufficiently inspiring project that I decided that I wanted to build more things on it. I wrote an entire grant about this and so on, but it started out with Flora coming to me, having found a couple papers about these models that I had not heard of and wanting to work with them. And so the impetus of an Oxford undergraduate actually played a big role in this particular thread of research that I continue to do. So hopefully you'll also have the experience of driving some of your mentors into new directions that they would not have thought of. I mean, that's one of the best reasons to, working with students is one of my favorite things, and this is one of the really great reasons to do it. Okay, so I wanted to stress that because this is, and this also is in Physical Review, so we're sticking with the same journal apparently. All right, so network structure can have a major effect on dynamics, including how many opinion groups form and how long they take to form. And so what we do is that at each discrete time, we select a pair of agents uniformly at random among those who are adjacent to the network. So this is selecting a uniformly at random edge, and they compromise if they're close enough, and otherwise they don't. And then you can ask these various questions. I'm going to show a larger version of the screenshotted equations on the next slide to make this easier. So it's blurry, so I should have done a better job of screenshot, but let me show you how this works. So time I have discretized, but I'm only updating actually one pair of nodes at once. Xi is telling me the opinion of node I. Xj is telling me the opinion of node j. So Xi of t is their opinion at time t, and Xi of t plus 1 is their opinion at time t plus 1. And if they are sufficiently close, so delta ji is the opinion of node j minus the opinion of node I, okay? If they are sufficiently close, so there's this parameter c, I update my opinion proportional to this difference and this other parameter m. And otherwise, I stay the same. And node j does the same. And to note here, these indices ji versus ij, the reason they're different is because one of them is larger than the other. And so this is necessarily, so one of them is xj minus xi, and the other is xi minus xj, right? That's necessarily true. But we're compromising by the same amount if we're close enough. And otherwise, we're not doing anything. And you can have variants of this where, somebody might be particularly stubborn, and so they compromise less, so their m could be lower, or they might have heterogeneous values of C. So there's various ways of making this more complicated. I mean, it's hard enough without doing that, but there are various ways of making it more complicated. So one example Okay, we're not going to go through this whole slide, but I want to show one thing. Let's look at the lower right. So there's 1,000 nodes here. And the vertical axis is the confidence bound. So if I'm higher on the vertical axis, I am more likely to be willing to compromise. And the horizontal axis is the amount by which I compromise if I do it. And then what's being shown with the color is how long it takes to converge, all the way up to not converging. And if you look over here, you see what looks like a curve. And someone actually in a different paper subsequent to us has found an approximate analytical expression for this curve using what's called a mean field theory, which is kind of related. Mean field theories in these models are related to kinetic models for any of you who've seen that. Kind of has that sort of flavor. But there's actually an approximate expression for this curve that's dividing the kind of shorter convergence time to longer convergence time in this particular type of network. Okay, one of the things that we did more recently, so this is now with my former postdoc, Heather Brooks, who's now faculty at Harvey Mudd. This is at what's known as, it's a liberal arts type school. They don't really have schools like that in the UK, but it's an undergraduate serving institution. Also appeared in a physics journal, though a slightly different one. And we took a bounded confidence mechanism and we added media to it. And so here, instead of having individuals interact with each other, think of my seeing a tweet and my choosing whether or not to retweet it. Okay, so now we're going to compare my opinion to the opinion of the tweet, which is the opinion of whoever is tweeting it, say. And if we're close enough, I will retweet it and also compromise a bit. And otherwise I will not. Okay, so the same type of mechanism, but now we're thinking of me interacting with some content online. And we actually considered distance both in ideology space, which is the example I was showing earlier, but also potentially the level of quality of the content. So if something is close to me in opinion, I am willing to have it be lower quality content, and maybe I'll retweet it anyway. But if it's very far from me in opinion, the content better be really high quality for me to think about retweeting it, right? And again, it's a toy, but it's not completely crazy. And then we have a certain type of nodes. In some papers, they call them zealots, but we were actually thinking of media. So we call them media nodes. They cannot change their opinion in our model. They can influence others, but cannot be influenced. Again, that's an assumption, right? I mean, all these things are simplifying assumptions. So that's what we do. So one of the things that we found, so this is a follower, again, sorry, it's blurry, followers per media account, number of media accounts. And this is a measure of how much opinions changed. I haven't shown you the definition of this, but it's a measure of how much opinions changed. And the thing that's interesting is that you've got this stripe. We don't know how to prove this, but we find this with many networks. I think there is an analytical calculation that we don't know how to do to find why this structure occurs. So we don't understand why this structure occurs. But there appears to be this band so that if you have like a moderate number of followers per media account and a moderate number of accounts, this appears to be the way you get the strongest influence. The intuition, which is not a complete intuition, is that echo chambers can form too early if, for instance, there's too many followers. And if the echo chambers form too early, overall, you'll have less influence. So something like that. But I mean, this is, you know, hand wavy, right? We don't have like a proper explanation for this. Okay, so one of the things that we did is that we took hand curated quality and opinion values from the Ad Fontes media bias chart to seed our media nodes with particular opinions. And so we've got opinions here. We do -1 to 1, so all the way to the left, all the way to the right, and quality values from 0 to 1. So clickbait on the bottom and like really sophisticated stuff on the top. So we put these nodes in the network and we see what they do. The size of the nodes is proportional to the number of followers they had on Twitter. Okay, and so those numbers of followers show up then in the model so they can influence more people in a direct way. I think the colors are just chosen for visual ease rather than meaningfulness. And then we've labeled the 5 that have the most followers. And if you take a look at what happens, So we start with people just having opinions that are chosen at random. So this is what they're currently tweeting. And so they're currently tweeting stuff that's chosen at random, and they're chosen with maybe a random quality value. And then we look at the end what they're tweeting. And what they're tweeting at the end is that you've got one echo chamber that's kind of around here, where you've got, you know, pretty high quality content that's pretty moderate. And you've got one echo chamber that's around here. How subtle should I be? That's doing pretty low content, quality content that's on the right. Now, this was hand curated, right? So we put this into the system. The idea, though, is that if I put something like this into the system and I have this simplistic mechanism, you see something that comes out that at a toy level seems pretty reasonable, right? So this mechanism is doing something that at least at a toy level seems reasonable. Okay. So I'm going to give some conclusions and give a comment a little bit on stuff we're doing now. So this is something, I hope I've convinced you that this is relevant for physics. There's lots of physicists who study this. I'm not I'm a little bit of a physicist, but I'm more of a mathematician, but I still publish a lot of this in physics journals. So maybe some of you will be interested in this. There are people within the math department at Oxford who study topics like this. So Renaud Lambiot is one good choice. I know some of you may not yet have physics projects. People in the Math Institute can supervise undergraduate physics majors in Oxford. I supervised several MPhys projects when I was in Oxford. And so I don't know if there's anybody in physics at Oxford who works on this, but if this is something that interests you, you know, Renaud Lambiot and some others in the Math Institute can be people who supervise an MPhys project. So this is something that you could work on if you're interested. And obviously for grad school and so on, the opportunities there are certainly available. Okay, so hopefully I've argued not just that there's some relation to physics, but there's a lot of cool stuff when doing this, and that there are interesting things to do, and that even taking these very simplistic models, that there's stuff to do. And I've shown you mostly numerics, but there's some analytical things that people can do as well. It's more of a struggle, but it's possible. I've given you flavors of 3 different models, and illustrated them through things that we happen to have done with them. And a key question that's arisen in all these is, how does network structure affect some process that occurs on the network? Is there a consensus? If so, how long does it take to get there? How many opinion groups do you have at steady state? If you have a certain parameter, do you have phase transitions? We have things that numerically look like phase transitions. We didn't prove that they were phase transitions, but they certainly look like phase transitions. And then we have some other stuff that's going on with a set of current and former students and postdocs. And so you'll see some names that showed up a little bit earlier in various guises, although I think I went through most of them pretty quickly. One of them is to put this on hypergraphs. What that means is to have more than 2 people interact at once, have many people interacting at once. So how does this type of model work when more than 2 people are interacting at once? So that's what this paper is about. And then there's a couple things that are in preparation. One of them is how to actually study cascades in these bounded confidence dynamics. Cascades were more of a threshold model thing, but we've actually figured out a way to study them in bounded confidence dynamics. Think of things being retweeted a lot, that type of cascade. So we're currently writing that up. We are also writing up a version that has these opinions on networks with more than one type of edge. So sharing on more than one social media at once is what you should think about in terms of intuition. So again, some of the same authors, I haven't introduced all of them to you. And then we have an adaptive bounded confidence model where you can have rewiring. And that's kind of funky because it's not obvious how to even measure what it means for an edge to be discordant. And so we've had to be clever about how we want to do that and how that affects the dynamics. And so that's what that one is. And I can give you more details about some of these, but these are some things that are currently in progress. Okay, and with that, I will quit. And I see some things in the chat that I should look at.
Okay, so whoever has questions for Professor Porter, leave them in the group chat. We have two already. Okay,
so yeah, let me try that. So let me first go to one of the slides that actually showed some of these things. And so the first question was, in the voter model, what is a natural examiner rewiring? What would that naturally model? Okay, so this is an interesting question for several reasons. And actually, I'm going to go one slide earlier because I think that explains it a little bit more. So there's 3 types of rewirings we show here. Now, the rewiring, the idea is that I'm arguing with someone. And our opinion is, our opinion is, say, very different from each other. And sometimes you're just going to stop interacting, right? So the thing that you're modeling with choosing to rewire in some form in the first place is, instead of, well, in the voter model, changing your opinion entirely, in other models, compromising your opinion, is to just break a friendship or break a tie. Now, the actual rewiring strategy, this is much less motivated. What people have chosen are the simplest possible ones because that's the best we know how to do. And we struggle to even work with those mathematically. And I think that's really the only motivation for most of those. Those are not really, like, I don't form a friendship with a random friend, right? Like, that's not what I do, right? So that's a mathematical artifact that allows you to study something. Now, the unfriending, I think, is more motivated, right? The rewire to none and unfriending, if someone pisses me off on Facebook, sorry, that's a technical term. If someone angers me on Facebook and I unfriend them, then that's, that, I mean, not that that happens often necessarily, but that's already well motivated. But the rewire to random, rewire to same, it's because people know how to work with them. And you're going to find this a lot when you're modeling stuff, right? Sometimes you model things and make a choice because it's realistic. And sometimes you make a choice because, well, this is what you know how to do. And it's better than not doing anything. And we struggle to make it gradually more realistic. And when it comes to putting methods of adaptation in these network models, that is a big struggle in the literature right now. How do you make it more realistic, but still have something that you can work with, especially if you're going to put in some theory and not just do numerics, or not just have a complicated model with way too many parameters? Okay, the next question. Oh,
also,
sorry.
on that point, so Q is a nonlinearity parameter. Is there an intuitive way to interpret that in terms of what we're doing with unfriending and stuff?
This would interpret the probability of the relative amount by which do I do a rewiring step, or do I do a change opinion step.
Okay.
So I don't think I can motivate it too much from the point of view of social science. I think the best motivation is to think of it like tuning a knob, like temperature or chemical potential or whatnot. What we wanted to do, and I would have to look through my old discussions with my students, like this was the bulk of a PhD thesis of one of my students. I think the motivation was to want to have different probabilities of how often do I rewire and how often do I change opinions, and just to ask a question which is much more, sort of theoretical in nature. What happens to the model as I do this? I don't think that our question at that point was really meant as a social question. Okay. So the next question, in the voter model, what is it? Oh, no, sorry, that's the question I already asked. What is the intuitive interpretation of a phase transition in these scenarios? Okay, so this will depend on what one is studying, but in this particular case, it will mean if I have small q, right? So q is telling me, I have never told you the values of sigma, so it kind of matters. So sigma is going to be less than 1. Right? Sigma is going to be less than 1 because I want this to be a probability. And so if I have large Q, then I'm going to get more and more towards changing opinion. Okay? And if I have small Q, I'll get more and more towards rewiring. And so with small Q, I'm more likely to get echo chambers. So what's happening here is that I'm going to get these small echo chambers versus, well, I end up getting this 50-50 business. And so it's like, okay, at t goes to infinity, do I have both groups still evenly present? Or, do I actually have one group dominating and then some small echo chambers? This is going to be harder to explain, but I mean, in this case, and I haven't told you what type of network structure it is, I get one group dominating in the middle, and I get some notion of echo chambers at the bottom, and I get some notion of echo chambers here at the bottom there. But what it's also saying is that this can get really complicated really quickly. Yeah. What a lot of physicists will try to do, and this gets away from the social questions, they will try to look at the nature of the transitions. Is it first order? Is it continuous? Is it discontinuous? Is it hybrid? Right? Like I think this one may be a hybrid transition. So they start classifying the phase transitions in this hierarchy. I think it's Ehrenfest, it's right after Ehren, but anyway, there's this hierarchy of phase transitions into which quantities are smooth and which are not. And so the physicists who work on these problems, they find that different variants of the models have phase transitions of a different physics style, regardless of what they mean. And so a lot of work in the physics literature kind of devolves into that. Now, my own view is that that tends to depart from the social questions. And so I don't tend to ask that particular question as much in my own work, but there is a lot of work that really gets into the sort of physics structure.
Yeah.
Would I be able to share that link? Yes, let me go ahead and do that. There is a version of these slides posted on SlideShare. So this is the actual link. So maybe I'll give you a chance to take a screenshot, but you can also find the slides directly on SlideShare.
Yeah, I can arrange for it to be posted in the event as well.
Okay, good. But it's almost completely the same slides. And then since a couple of these people showed up, this was a short course that we did for the American Mathematical Society this January. And so a bunch of lectures are posted, a bunch of videos are posted, some panel discussions are posted. And this was oriented more towards mathematicians than for physicists. So it's a slightly different orientation, but there's a lecture on like an introduction to networks that, so Heather Brooks did that one. There is a lecture on introduction to complex systems, which Al Volkening did. And then there's a lecture on introduction to topological data analysis, which Michelle Fung did. So different, and that topic's another topic I spend time on, didn't show up in this talk. Michelle's name showed up a lot because of co-authoring a bunch of papers at the end on this other topic. And then there's some panel discussions with people from social science and math. And then I did a lecture on data ethics, which if you think about things like AI and horrible things that it can do in terms of propagating biases is something that, okay, so I did it for mathematicians, but physicists should do it as well, because I think a lot of physicists get into machine learning for jobs if they don't stay in academia as well. Okay, is it useful to consider directed graphs? Right, yes, it is. In fact, and I went through this, I did not actually mention it, but it was hinted on the slide, or stated on the slide, but I didn't go into it. When we were thinking about influence of media, we did actually have directed graphs, and that was how we encoded media not being influenced by others. But yes, it is absolutely, directed graphs are very relevant. You can put asymmetries in various ways. Twitter is a good example. Instagram is a good example. I mean, Twitter was more intuitive for the question we were asking, but yes. Okay. So the answer is, as a technical point, by the way, if you're doing certain types of methods, directed graphs will get more complicated. So if you're doing what are called spectral methods, so based on finding, say, eigenvalues that are associated with a graph, associated with matrix representations of the graph. If it's directed, you have an asymmetric matrix, which will imply that the spectrum does not have to be real. And there are certain methods that want the spectrum to be real. So on a technical point, directed graphs will be harder for certain things. Not what we did necessarily, but for others. Okay, the next question. In the media influence part, or in most network models, how is it conducted? Okay, so is the data collected from media and then plotted? Okay, so these papers that I brought up were mostly numerical computation and were a simulation of a dynamical process on a system. But other ones can be analytical, like deriving mean field models. There's a little bit of analytics in a couple of these papers. We did not do data analysis in the sense of empirical data in these papers, but others can be data analysis. When we do clustering of things, or if we want to try to evaluate it compared to real data. But these particular ones happen to be mostly numerical computations of models. Some of the networks that we use were empirical data, but that's not really a serious, that's like a minor use of empirical. It says, I have a network from data, like if I have a couple of data from old datasets from old Facebook networks. I have a data set, I encode it in my computer, and now my simulation no longer cares that it came from empirical data versus generating it from a model. And so I don't think I showed you our examples in which we use that, but those papers do have examples like that. but that's not the same as saying, looking at actual spreading process on an empirical data set and comparing my spreading process to theirs, right? Like that would be a much more serious one. This might entail a larger discussion because this gets into the day-to-day of, do you want to do a project in which you prove theorems? Do you want to do a project in which you develop a model? Do you want to do a project in which you do numerical computations? Because this really has a big influence on what your project is like when you make choices like this. So the next one, you're welcome and thank you for the compliment. Have I compared the performance of models to scenarios like voter models to real life data? Okay. So this has mostly been theoretical. These models, many of them are actually very hard to validate. And one of the reasons, I didn't bring up this issue, but it's a big issue. And one of the reasons that they're very hard to validate, let's say someone has an opinion between -1 and 1. Let's say my opinion is -0.75. How do you measure that?
Yeah.
Like, okay, great, I'm on the left. How do you measure that? One of the big reasons that I've been moving into bounded confidence models, and the paper with influence of media actually gets into this, even though that's not what I focused on today. It's hard to validate my opinions or anyone's opinions. But what I can validate is spreading processes, the spreading patterns of something on Twitter. So I could ask, does this model produce spreading patterns that are realistic? Because spreading patterns, a spreading of a tweet is a discrete event. I can measure that. And so this is the direction we're going. And this, in fact, is exactly why we are, right, or what's all, I mean, the paper's partly written, why are we doing that paper? What this is going to be about is what can you measure in spreading things on networks. Now, it's not going to have the comparison, but it's going to have an idea of what should we measure in the structure of this. It's actually spreading kind of, tree, it's really directly acyclic graph. But we want to measure that, and we want to look at if the structure of the networks we produce that describe spreading are similar to actual retweet trees. Okay, so we're moving in this direction, but we're not there yet. And you can notice there's a lot of bounded confidence papers. I have an entire grant to do bounded confidence models. And one of our goals is to actually do this type of validation to the extent possible, although there's really a bunch of fundamental model building that we're trying to do along the way. So Leo, you're welcome. I think the only two, oh no, wait, there's a couple of other things here. Okay, so you're welcome to all the people who asked me stuff, who complimented me. I always appreciate that, and I'm glad that this worked out well. And then, you can look at the recorded version of this talk that I gave at Nordita last week, and even though the slides are the same, you'll notice that I geared the words differently to the audience if you want a different version of the talk. So same slides, but the actual focus was different despite that. All right, how do the results of the voter model change when you replace the underlying network, and how are the dynamics affected by the small world property? Okay, so I have not done, this particular paper did not have, okay, so let me actually first back up because, okay, so Sam, you've seen some of these words that I did not mention. Let me tell other people what some of these words mean to give a context to the question. So Erdos-Renyi I did introduce. Watt-Strogatz networks are a very famous model that are sometimes called a small world model. And what you do is you take a ring lattice, although you connect to more than just the direct nearest neighbors, and then you rewire those to get some shortcuts. And so locally you have this clustering that's very lattice-like because you started with a lattice, but then you have these long-range shortcut edges. And it's small world in the sense of you've got these very small paths, so 6 degrees of separation type small worlds. And so you have local clustering and you have shortcuts to different part of the network. And then a Barabashi-Albert type network is what's known as a preferential attachment network. The rich get richer. Something has a lot of nodes and a new node attaches to it. Like if I have a new website, I might link to Google, for instance. But if I have a new website, I'm probably not going to link. Okay, I was about to say to one of my students' web pages, but I actually probably would link to one of my students' web pages. My students are watching this. I'm sorry. No, anyway, I mean, it's a rich get richer mechanism. So this leads to very hub and spoke like networks. Okay, so those network structures are very different. And generically, if I put the same process on a network with a different structure, I expect to get different dynamics. And the one sense in which I think I showed you this a bit, though I didn't explain it fully, was when I changed to Erdos-Renyi, of course, these are different types of networks than the ones that were brought up in the question. But when I changed Erdos-Renyi to these types of networks, the phase transitions took on a different character. And so you would ask, okay, well, what happens, right? So clearly, so, high, low versus low-ish, high, low, right? And I ran the same process, but we changed to different network structure. There have been studies on voter models on the Watts-Strogatz and Barabashi-Albert networks. I don't remember how those changed the structure, but there have been studies that have used those networks, and maybe they refer to them in this Redner article that I mentioned. The intuition behind, say, the Watts-Strogatz style is that when you're lattice-like, you only have a small number of neighbors, and so only those neighbors will do something, but then you would expect that the shortcuts would allow an opinion on a slower time scale to change an opinion elsewhere in the network. That's what I would expect, but I don't know if that's what actually happens, and I don't remember, but people have studied this.
And I think that was the last question. Yeah.
Okay.
Yeah. So thanks, everyone. People seem to have really enjoyed the talk. So everyone,
Great. I'm
thank
glad.
Professor Porter. And yeah, thank you everyone for joining us.
Yeah, thanks a lot.
Yeah.
And thank you, and thank you very much for having me. I hope to visit Oxford in person soon, and then maybe I'll meet some of you if you're, well, those of you who haven't graduated by that point.
Yeah, if you do, as the Oxford Society and the Invariant Society with Vlad, we owe you a meal in Oxford. So
I look forward to it.
Yeah.
All
so
right.
Thank you.
Yep, you're welcome. Right. Bye.
Bye, everyone.
Thank you. Bye.